Sun at Wikipedia, the free encyclopedia, at en.wikipedia.org. The text in this article is current as of the 7th of June 2021. This article contains the following sections: 1. Name and etymology. 2. General characteristics. 3. Sunlight. 4. Composition. 5. Structure and fusion. 6. Magnetic activity. 7. Life phases. 8. Motion and location. 9. Theoretical problems. 10. Observational history. 11. Observation and effects. 12. Planetary system. And 13. Religious aspects. The Sun is the star at the centre of the solar system. It is a nearly perfect sphere of hot plasma, heated to incandescence by nuclear fusion reactions in its core, radiating the energy mainly as visible light and infrared radiation. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometres, or 864,000 miles, or 109 times that of Earth. Its mass is about 330,000 times that of Earth. It accounts for about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, about 73%, the rest is mostly helium, about 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. There's then an image, pictured in visible light with solar filter in 2013, with sunspots and limb darkening. And another image, false colour image taken in 2010 as seen in ultraviolet light with a wavelength of 30.4 nanometers. There's then an info box containing lots of data about the Sun. The Sun is a G-type main sequence star, G2V, based on its spectral class. As such, it is informally and not completely accurately referred to as a yellow dwarf. Its light is closer to white than yellow. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered around the centre, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun's core fuses about 600 million tons of hydrogen into helium every second, converting 4 million tons of matter into energy every second as a result. This energy, which can take between 10,000 and 170,000 years to escape the core, is the source of the Sun's light and heat. When hydrogen fusion in its core has diminished to the point at which the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature while its outer layers expand, eventually transforming the Sun into a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury and Venus and render Earth uninhabitable, but not for about 5 billion years. After this, it will shed its outer layers and become a dense type of cooling star known as a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognised since prehistoric times. The Sun was thought of by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of solar calendars, one of which is the Gregorian calendar, the predominant calendar in use today. Section 1. Name and etymology. Please note that almost all of my attempts to speak words in other languages should be taken with a pinch of salt. The English word sun developed from Old English sun. Cognates appear in other Germanic languages, including West Frisian sin, Dutch zon, Low German sun, Standard German son, Bavarian sunna, Old Norse sunna, and Gothic sunno. All these words stem from Proto-Germanic sunnon. This is ultimately related to the word for sun in other branches of the Indo-European language family, though in most cases a nominative stem with an L is found, rather than the genitive stem in N, as for example in Latin sol, Greek helios, Welsh hol, and Russian sonce, as well as Sanskrit svar and Persian khvar. Indeed, the L stem survived in Proto-Germanic as well, as soelan, which gave rise to Gothic saul, alongside sunno, and Old Norse prosaic sol, alongside poetic sunna, and through it the words for sun in the modern Scandinavian languages, Swedish and Danish solen, Icelandic solen, etc. In English, the Greek and Latin words occur in poetry as personifications of the sun, Helios and Sol, while in science fiction, Sol may be used as a name for the sun to distinguish it from other stars. The term Sol with a lowercase s is used by planetary astronomers for the duration of a solar day on another planet, such as Mars. The principal adjectives for the sun in English are sunny, for sunlight, and, in technical contexts, solar, from Latin sol, the latter found in such terms as solar day, solar eclipse, and solar system, occasionally sol system. From the Greek helios comes the rare adjective heliac. The English weekday name Sunday stems from Old English sunnedag, sun's day, a Germanic interpretation of the Latin phrase dies solis, itself a translation of the Greek hemera heliou, day of the sun. Section 2. General characteristics. The Sun is a G-type main sequence star that comprises about 99.86% of the mass of the solar system. The Sun has an absolute magnitude of positive 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. The Sun is a population 1, or heavy element rich, star. The formation of the Sun may have been triggered by shock waves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population 2, heavy element poor stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of negative 26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of negative 1.46. One astronomical unit, about 150 million kilometers or 93 million miles, is defined as the mean distance of the Sun's centre to the Earth's centre, though the distance varies as Earth moves from perihelion in January to aphelion in July. The distances can vary between 147,098,074 kilometers at perihelion and 152,097,701 kilometers aphelion, and extreme values can range from 147,083,346 kilometers to 152,112,126 kilometers. At its average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 19 seconds, while light from the closest point of the Sun and Earth takes about 2 seconds less. The energy of this sunlight supports almost all life on Earth by photosynthesis, and drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. For the purpose of measurement, the Sun's radius is considered to be the distance from its centre to the edge of the photosphere, the apparent visible surface of the Sun. By this measure, the Sun is a near-perfect sphere, with an oblateness estimated at about 9 millionths, which means that its polar diameter differs from its equatorial diameter by only 10 kilometers, 6.2 miles. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from the Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. Viewed from a vantage point above its North Pole, the Sun rotates counterclockwise around its axis of spin. Section 3. Sunlight, for which the main article is sunlight. There's an image of the Sun as seen from the Earth's surface. The solar constant is the amount of power that the Sun deposits per unit area that is directly exposed to sunlight. The solar constant is equal to approximately 1,368 watts per square metre at a distance of 1 astronomical unit from the Sun, that is, on or near Earth. Sunlight on the surface of Earth is attenuated by Earth's atmosphere, so that less power arrives at the surface, closer to 1,000 watts per square metre, in clear conditions when the Sun is near the zenith. Sunlight at the top of Earth's atmosphere is composed, by total energy, of about 50% infrared light, 40% visible light, and 10% ultraviolet light. The atmosphere in particular filters out over 70% of solar ultraviolet, especially at the shorter wavelengths. Solar ultraviolet radiation ionizes Earth's dayside upper atmosphere, creating the electrically conducting ionosphere. The Sun emits light across the visible spectrum, so its colour is white, with a CIE colour space index near 0.3 when viewed from space or when the Sun is high in the sky. The solar radiance per wavelength peaks in the green portion of the spectrum when viewed from space. When the Sun is low in the sky, atmospheric scattering renders the Sun yellow, red, orange, or magenta. Despite its typical whiteness, most people mentally picture the Sun as yellow. The reasons for this are the subject of debate. The Sun is a G2V star, with G2 indicating its surface temperature of approximately 5,778 Kelvin, or 5,505 degrees Celsius, 9,941 degrees Fahrenheit, and V that it, like most stars, is a main sequence star. The average luminance of the Sun is about 1.88 gigacandela per square metre, but as viewed through Earth's atmosphere, this is lowered to about 1.44 gigacandela per square metre. However, the luminance is not constant across the disk of the Sun. Limb darkening. Section 4. Composition. There's an image, which is a false colour wiggle animation of the Sun. Then a second image. Normally the Sun does not make gamma rays, but a flare on June the 15th, 1991 caused this gamma ray observation by the Comptel instrument on the Compton Gamma Ray Observatory. Neutrons from the Sun collided with the interstellar medium to produce gamma rays. Then a third image, 1973 solar flare as recorded by Skylab. See also the article Molecules in Stars. The Sun is composed primarily of the chemical elements hydrogen and helium. At this time in the Sun's life, they account for 74.9% and 23.8% of the mass of the Sun in the photosphere respectively. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, roughly 1% of the Sun's mass, carbon, 0.3%, neon, 0.2%, and iron, 0.2%, being the most abundant. The Sun's original chemical composition was inherited from the interstellar medium out of which it formed. Originally, it would have contained about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and most of the helium in the Sun would have been produced by Big Bang nucleosynthesis in the first 20 minutes of the universe, and the heavier elements were produced by previous generations of stars before the Sun was formed, and spread into the interstellar medium during the final stages of stellar life and by events such as supernovae. Since the Sun formed, the main fusion process has involved fusing hydrogen into helium. Over the past 4.6 billion years, the amount of helium and its location within the Sun has gradually changed. Within the core, the proportion of helium has increased from about 24% to about 60% due to fusion, and some of the helium and heavy elements have settled from the photosphere towards the centre of the Sun because of gravity. The proportions of metals, heavier elements, is unchanged. Heat is transferred outward from the Sun's core by radiation rather than by convection. See radiative zone below. So the fusion products are not lifted outward by heat. They remain in the core, and gradually an inner core of helium has begun to form that cannot be fused because presently the Sun's core is not hot or dense enough to fuse helium. In the current photosphere, the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase, before nuclear fusion in the core started. In the future, helium will continue to accumulate in the core, and in about 5 billion years, This gradual build-up will eventually cause the Sun to exit the main sequence and become a red giant. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. The solar heavy element abundances described above are typically measured both using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperatures. These meteorites are thought to retain the composition of the protostellar Sun and are thus not affected by the settling of heavy elements. The two methods generally agree well. Section 4.1 Singly ionized iron group elements. In the 1970s, much research focused on the abundance of iron group elements in the Sun. Although significant research was done, until 1978 it was difficult to determine the abundances of some iron group elements, such as cobalt and manganese, via spectrography because of their hyperfine structures. The first largely complete set of oscillator strengths of singly ionized iron group elements were made available in the 1960s, and these were subsequently improved. In 1978, the abundances of singly ionized elements of the iron group were derived. Section 4.2 Isotopic composition. Various authors have considered the existence of a gradient in the isotopic compositions of solar and planetary noble gases, for example, correlations between isotopic compositions of neon and xenon in the Sun and on the planets. Prior to 1983, it was thought that the whole Sun has the same composition as the solar atmosphere. In 1983, it was claimed that it was fractionation in the Sun itself that caused the isotopic composition relationship between the planetary and solar wind-implanted noble gases. Section 5 Structure and Fusion, for which the main article is Standard Solar Model. There's an image, the structure of the Sun, and then a series of graphs for temperature profile in the Sun, mass inside a given radius in the Sun, density profile in the Sun, and pressure profile in the Sun. The structure of the Sun contains the following layers. Core, the innermost 20 to 25% of the Sun's radius, where temperature and pressure are sufficient for nuclear fusion to occur. Hydrogen fuses into helium, which cannot itself be fused at this point in the Sun's life. The fusion process releases energy, and the core gradually becomes enriched in helium. Radiative zone. Convection cannot occur until much nearer the surface of the Sun. Therefore, between about 20 to 25% of the radius and 70% of the radius, there is a radiative zone in which energy transfer occurs by means of radiation, photons, rather than by convection. Tachocline, the boundary region between the radiative and convective zones. Convective zone, between about 70% of the Sun's radius and a point close to the visible surface. The Sun is cool and diffuse enough for convection to occur, and this becomes the primary means of outward heat transfer, similar to weather cells which form in Earth's atmosphere. Because the Sun is a gaseous object, it does not have a clearly defined surface. Its visible parts are usually divided into a photosphere and atmosphere. Photosphere, the deepest part of the Sun which we can directly observe with visible light. Atmosphere, a gaseous halo surrounding the Sun, comprising the chromosphere, solar transition region, corona, and heliosphere. These can be seen when the main part of the Sun is hidden, for example, during a solar eclipse. Section 5.1 Core, for which the main article is Solar Core. The core of the Sun extends from the centre to about 20 to 25% of the solar radius. It has a density of up to 150 grams per cubic centimetre, about 150 times the density of water, and a temperature close to 15.7 million kelvins. By contrast, the Sun's surface temperature is approximately 5,800 kelvins. Recent analysis of SOHO mission data favours a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy has been produced by nuclear fusion in the core region through a series of nuclear reactions called the P-to-P, or proton-to-proton, chain. This process converts hydrogen into helium. Only 0.8% of the energy generated in the Sun comes from another sequence of fusion reactions called the CNO cycle, though this proportion is expected to increase as the Sun becomes older. The core is the only region in the Sun that produces an appreciable amount of thermal energy through fusion. 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers, finally to the solar photosphere, where it escapes into space through radiation, photons, or advection, massive particles. The proton-proton chain occurs around 9.2 times 10 to the power of 37 times each second in the core, converting about 3.7 times 10 to the power of 38 protons into alpha particles, helium nuclei, every second, out of a total of about 8.9 times 10 to the power of 56 free protons in the Sun, or about 6.2 times 10 to the power of 11 kilograms per second. Fusing 4 free protons, hydrogen nuclei, into a single alpha particle, helium nucleus, releases around 0.7% of the fused mass as energy, so the Sun releases energy at the mass-energy conversion rate of 4.26 million metric tons per second, which requires 600 metric megatons of hydrogen, for 384.6 yottawatts, 3.846 times 10 to the power of 26 watts, or 9.192 times 10 to the power of 10 megatons of TNT per second. The large power output of the Sun is mainly due to the huge size and density of its core, compared to Earth and objects on Earth, with only a fairly small amount of power being generated per cubic meter. Theoretical models of the Sun's interior indicate a maximum power density, or energy production, of approximately 276.5 watts per cubic meter at the centre of the core, which is about the same power density inside a compost pile. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation. And a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate. Section 5.2 Radiative Zone, for which the main article is Radiative Zone. From the core out to about 0.7 solar radii, thermal radiation is the primary means of energy transfer. The temperature drops from approximately 7 million to 2 million kelvins with increasing distance from the core. This temperature gradient is less than the value of the adiabatic lapse rate and hence cannot drive convection, which explains why the transfer of energy through this zone is by radiation instead of thermal convection. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold, from 20 grams per cubic centimetre to 0.2 grams per cubic centimetre, between 0.25 solar radii and 0.7 solar radii, the top of the radiative zone. Section 5.3 Tachocline, for which the main article is tachocline. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and the differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. Presently, it is hypothesized, see solar dynamo, that a magnetic dynamo within this layer generates the Sun's magnetic field. Section 5.4 Convective Zone, for which the main article is Convection Zone. The Sun's convection zone extends from 0.7 solar radii, 500,000 kilometers, to near the surface. In this layer, the solar plasma is not dense enough or hot enough to transfer the heat energy of the interior outward via radiation. Instead, the density of the plasma is low enough to allow convective currents to develop and move the Sun's energy outward towards its surface. Material heated at the tachocline picks up heat and expands, thereby reducing its density and allowing it to rise. As a result, an orderly motion of the mass develops into thermal cells that carry the majority of the heat outward to the Sun's photosphere above. Once the material diffusively and radiatively cools just beneath the photospheric surface, its density increases, and it sinks to the base of the convection zone, where it again picks up heat from the top of the radiative zone and the convective cycle continues. At the photosphere, the temperature has dropped to 5,700 Kelvin, and the density to only 0.2 grams per cubic metre, about 1/6000th the density of air at sea level. The thermal columns of the convection zone form an imprint on the surface of the Sun, giving it a granular appearance called the solar granulation at the smallest scale, and supergranulation at larger scales. Turbulent convection in this outer part of the solar interior sustains small-scale dynamo action over the near-surface volume of the Sun. The Sun's thermal columns are Binar cells that take the shape of roughly hexagonal prisms. Section 5.5, Photosphere, for which the main article is Photosphere. There's a graph. The effective temperature, or black body temperature, of the Sun, 5,777 Kelvin, is the temperature a black body of the same size must have to yield the same total emissive power. There's another image, high-resolution image of the Sun's surface, taken by the Daniel K. Inouye Solar Telescope. The visible surface of the Sun, the photosphere, is the layer below which the Sun becomes opaque to visible light. Photons produced in this layer escape the Sun through the transparent solar atmosphere above it and become solar radiation, sunlight. The change in opacity is due to the decreasing amount of H- ions, which absorb visible light easily. Conversely, the visible light we see is produced as electrons react with hydrogen atoms to produce H- ions. The photosphere is tens to hundreds of kilometers thick and is slightly less opaque than air on Earth. Because the upper part of the photosphere is cooler than the lower part, an image of the Sun appears brighter in the centre than on the edge or limb of the solar disk, in a phenomenon known as limb darkening. The spectrum of sunlight has approximately the spectrum of a black body radiating at 5,777 Kelvin, interspersed with atomic absorption lines from the tenuous layers above the photosphere. The photosphere has a particle density of about 10 to the power of 23 per cubic metre, about 0.37% of the particle number per volume of Earth's atmosphere at sea level. The photosphere is not fully ionised. The extent of ionisation is about 3%, leaving almost all of the hydrogen in atomic form. During early studies of the optical spectrum of the photosphere, some absorption lines were found that did not correspond with any chemical elements then known on Earth. In 1868, Norman Lockyer hypothesized that these absorption lines were caused by a new element that he dubbed helium, after the Greek sun god Helios. 25 years later, helium was isolated on Earth. Section 5.6, Atmosphere. See also solar corona and coronal loop. There's an image. During a total solar eclipse, the solar corona can be seen with the naked eye during the brief period of totality. During a total solar eclipse, when the disk of the Sun is covered by that of the Moon, parts of the Sun's surrounding atmosphere can be seen. It is composed of 4 distinct parts: the chromosphere, the transition region, the corona, and the heliosphere. The coolest layer of the Sun is a temperature minimum region extending to about 500 kilometers above the photosphere and has a temperature of about 4,100 Kelvin. This part of the Sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water, which can be detected via their absorption spectra. The chromosphere, transition region, and corona are much hotter than the surface of the Sun. The reason is not well understood, but evidence suggests that Alfvén waves may have enough energy to heat the corona. Above the temperature minimum layer is a layer about 2,000 kilometers thick, dominated by a spectrum of emission and absorption lines. It is called the chromosphere, from the Greek root chroma, meaning colour, because the chromosphere is visible as a coloured flash at the beginning and end of total solar eclipses. The temperature of the chromosphere increases gradually with altitude, ranging up to around 20,000 Kelvin near the top. In the upper part of the chromosphere, helium becomes partially ionised. There's an image taken by Hinori's Solar Optical Telescope on the 12th of January 2007. This image of the Sun reveals the filamentary nature of the plasma connecting regions of different magnetic polarity. Above the chromosphere, in a thin, about 200 kilometre, transition region, the temperature rises rapidly from around 20,000 Kelvin in the upper chromosphere to coronal temperatures closer to 1 million Kelvin. The temperature increase is facilitated by the full ionization of helium in the transition region, which significantly reduces radiative cooling of the plasma. The transition region does not occur at a well-defined altitude. Rather, it forms a kind of nimbus around chromospheric features such as spicules and filaments, and is in constant chaotic motion. The transition region is not easily visible from Earth's surface, but is readily observable from space by instruments sensitive to the extreme ultraviolet portion of the spectrum. The corona is the next layer of the Sun. The low corona, near the surface of the Sun, has a particle density of around 10 to the power of 15 per cubic metre to 10 to the power of 16 per cubic metre. The average temperature of the corona and solar wind is about 1 million to 2 million Kelvin. However, in the hottest regions it is 8 million to 20 million Kelvin. Although no complete theory yet exists to account for the temperature of the corona, at least some of its heat is known to be from magnetic reconnection. The corona is the extended atmosphere of the Sun, which has a volume much larger than the volume enclosed by the Sun's photosphere. A flow of plasma outward from the Sun into interplanetary space is the solar wind. The heliosphere, the tenuous outermost atmosphere of the Sun, is filled with the solar wind plasma. This outermost layer of the Sun is defined to begin at the distance where the flow of the solar wind becomes superalvinic, that is, where the flow becomes faster than the speed of Alvin waves, at approximately 20 solar radii, or about 0.1 astronomical units. Turbulence and dynamic forces in the heliosphere cannot affect the shape of the solar corona within, because the information can only travel at the speed of Alvin waves. The solar wind travels outward continuously through the heliosphere, forming the solar magnetic field into a spiral shape, until it impacts the heliopause more than 50 astronomical units from the Sun. In December 2004, the Voyager 1 probe passed through a shock front that is thought to be part of the heliopause. In late 2012, Voyager 1 recorded a marked increase in cosmic ray collisions and a sharp drop in lower energy particles from the solar wind, which suggested that the probe had passed through the heliopause and entered the interstellar medium, and indeed did so on the 25th of August 2012 at approximately 122 astronomical units from the Sun. The heliosphere has a heliotail, which stretches out behind it due to the Sun's movement. Section 5.7, Photons and Neutrinos. See also Solar Irradiance. High-energy gamma-ray photons initially released with fusion reactions in the core are almost immediately absorbed by the solar plasma of the radiative zone, usually after travelling only a few millimeters. Re-emission happens in a random direction and usually at slightly lower energy. With this sequence of emissions and absorptions, it takes a long time for radiation to reach the Sun's surface. Estimates of the photon travel time range between 10,000 and 170,000 years. In contrast, it takes only 2.3 seconds for the neutrinos, which account for about 2% of the total energy production of the Sun, to reach the surface. Because energy transport in the Sun is a process that involves photons in thermodynamic equilibrium with matter, the timescale of energy transport in the Sun is longer, on the order of 30 million years. This is the time it would take the Sun to return to a stable state if the rate of energy generation in its core were suddenly changed. Neutrinos are also released by the fusion reactions in the core, but, unlike photons, they rarely interact with matter, so almost all are able to escape the Sun immediately. For many years, measurements of the number of neutrinos produced in the Sun were lower than the theories predicted by a factor of 3. This discrepancy was resolved in 2001 through the discovery of the effects of neutrino oscillation. The Sun emits the number of neutrinos predicted by the theory, but neutrino detectors were missing 2/3 of them, because the neutrinos had changed flavour by the time they were detected. Section 6. Magnetic Activity. Section 6.1. Magnetic Field. See also Stellar Magnetic Field, Sunspots, List of Solar Cycles, and Solar Phenomena. There's an image, Visible Light Photograph of Sunspot, 13th of December 2006. Another image, a butterfly diagram showing paired sunspot patterns, Graph is of sunspot area. Another image. In this false colour ultraviolet image, the Sun shows a C3 class solar flare, white area on upper left, a solar tsunami, wave-like structure upper right, and multiple filaments of plasma following a magnetic field rising from the stellar surface. Then one last image. The heliospheric current sheet extends to the outer reaches of the solar system and results from the influence of the Sun's rotating magnetic field on the plasma in the interplanetary medium. The Sun has a magnetic field that varies across its surface. Its polar field is 1 to 2 Gauss, 0.0001 to 0.0002 Teslas, whereas the field is typically 3000 Gauss, 0.3 Tesla, in features on the Sun called sunspots, and 10 to 100 Gauss, 0.001 to 0.01 Teslas, in solar prominences. The magnetic field varies in time and location. The quasi-periodic 11-year solar cycle is the most prominent variation in which the number and size of sunspots waxes and wanes. Sunspots are visible as dark patches on the Sun's photosphere and correspond to concentrations of magnetic field where the convective transport of heat is inhibited from the solar interior to the surface. As a result, sunspots are slightly cooler than the surrounding photosphere, so they appear dark. At a typical solar minimum, few sunspots are visible, and occasionally none can be seen at all. Those that do appear are at high solar latitudes. As the solar cycle progresses towards its maximum, sunspots tend to form closer to the solar equator, a phenomenon known as Spurer's law. The largest sunspots can be tens of thousands of kilometers across. An 11-year sunspot cycle is half of a 22-year Babcock-Leighton dynamo cycle, which corresponds to an oscillatory exchange of energy between toroidal and poloidal solar magnetic fields. At solar cycle maximum, the external poloidal dipolar magnetic field is near its dynamo cycle minimum strength, but an internal toroidal quadrupolar field, generated through differential rotation within the trachycline, is near its maximum strength. At this point in the dynamo cycle, buoyant upwelling within the convective zone forces emergence of the toroidal magnetic field through the photosphere, giving rise to pairs of sunspots, roughly aligned east to west and having footprints with opposite magnetic polarities. The magnetic polarity of sunspot pairs alternates every solar cycle, a phenomenon known as the Hale cycle. During the solar cycle's declining phase, energy shifts from the internal toroidal magnetic field to the external poloidal field, and sunspots diminish in number and size. At solar cycle minimum, the toroidal field is, correspondingly, at minimum strength, sunspots are relatively rare, and the poloidal field is at its maximum strength. With the rise of the next 11-year sunspot cycle, differential rotation shifts magnetic energy back from the poloidal to the toroidal field, but with a polarity that is opposite to the previous cycle. The process carries on continuously, and in an idealized simplified scenario, each 11-year sunspot cycle corresponds to a change, then, in the overall polarity of the Sun's large-scale magnetic field. The solar magnetic field extends well beyond the Sun itself. The electrically conducting solar wind plasma carries the Sun's magnetic field into space, forming what is called the interplanetary magnetic field. In an approximation known as ideal magnetohydrodynamics, plasma particles only move along the magnetic field lines. As a result, the outward-flowing solar wind stretches the interplanetary magnetic field outward, forcing it into a roughly radial structure. For a simple dipolar solar magnetic field, with opposite hemispherical polarities on either side of the solar magnetic equator, a thin current sheet is formed in the solar wind. At great distances, the rotation of the Sun twists the dipolar magnetic field and corresponding current sheet into an Archimedean spiral structure called the Parker spiral. The interplanetary magnetic field is much stronger than the dipole component of the solar magnetic field. The Sun's dipole magnetic field of 50 to 400 microteslas at the photosphere reduces with the inverse cube of the distance, leading to a predicted magnetic field of 0.1 nanoteslas at the distance of Earth. However, according to spacecraft observations, the interplanetary field at Earth's location is around 5 nanoteslas, about 100 times greater. The difference is due to magnetic fields generated by electrical currents in the plasma surrounding the Sun. Section 6.2 Variation in Activity. There's an image, Solar Cycle Variations, measurements from 2005 of solar cycle variation during the previous 30 years. The Sun's magnetic field leads to many effects that are collectively called solar activity. Solar flares and coronal mass ejections tend to occur at sunspot groups. Slowly changing high-speed streams of solar wind are emitted from coronal holes at the photospheric surface. Both coronal mass ejections and high-speed streams of solar wind carry plasma and interplanetary magnetic field outward into the solar system. The effects of solar activity on Earth include auroras at moderate to high latitude, and the disruption of radio communications and electric power. Solar activity is thought to have played a large role in the formation and evolution of the solar system. With solar cycle modulation of sunspot number comes a corresponding modulation of space weather conditions, including those surrounding Earth where technological systems can be affected. In December 2019, a new type of solar magnetic explosion was observed, known as forced magnetic reconnection. Previously, in a process called spontaneous magnetic reconnection, it was observed that the solar magnetic field lines diverge explosively and then converge again instantaneously. Forced magnetic reconnection was similar, but it was triggered by an explosion in the corona. Section 6.3. Long-term change. Long-term secular change in sunspot number is thought, by some scientists, to be correlated with long-term change in solar irradiance, which, in turn, might influence Earth's long-term climate. For example, in the 17th century, the solar cycle appeared to have stopped entirely for several decades. Few sunspots were observed during a period known as the Maunder Minimum. This coincided in time with the era of the Little Ice Age, when Europe experienced unusually cold temperatures. Earlier extended minima have been discovered through analysis of tree rings and appear to have coincided with lower than average global temperatures. A recent theory claims that there are magnetic instabilities in the core of the Sun that cause fluctuations with periods of either 41,000 or 100,000 years. These could provide a better explanation of the ice ages than the Milankovitch cycles. Section 7. Life Phases, for which the main articles are Formation and Evolution of the Solar System and Stellar Evolution. The Sun today is roughly halfway through the most stable part of its life. It has not changed dramatically for over 4 billion years, and will remain fairly stable for more than 5 billion more. However, after hydrogen fusion in its core has stopped, the Sun will undergo dramatic changes, both internally and externally. Section 7.1. Formation. The Sun formed about 4.6 billion years ago from the collapse of part of a giant molecular cloud that consisted mostly of hydrogen and helium, and that probably gave birth to many other stars. This age is estimated using computer models of stellar evolution and through nucleocosmochronology. The result is consistent with the radiometric date of the oldest solar system material, at 4.567 billion years ago. Studies of ancient meteorites reveal traces of stable daughter nuclei of short-lived isotopes, such as iron-60, that form only in exploding, short-lived stars. This indicates that one or more supernovae must have occurred near the location where the Sun formed. A shock wave from a nearby supernova would have triggered the formation of the Sun by compressing the matter within the molecular cloud and causing certain regions to collapse under their own gravity. As one fragment of the cloud collapsed, it also began to rotate due to conservation of angular momentum and heat up with the increasing pressure. Much of the mass became concentrated in the centre, whereas the rest flattened out into a disk that would become the planets and other solar system bodies. Gravity and pressure within the core of the cloud generated a lot of heat as it accumulated more matter from the surrounding disk, eventually triggering nuclear fusion. HD 162826 and HD 186302 are hypothesized stellar siblings of the Sun, having formed in the same molecular cloud. Section 7.2. Main sequence. There's a diagram. Evolution of the Sun's luminosity, radius and effective temperature compared to the present Sun, after Rebus in 2010. The Sun is about halfway through its main sequence stage, during which nuclear fusion reactions in its core fuse hydrogen into helium. Each second, more than 4 million tons of matter are converted into energy within the Sun's core, producing neutrinos and solar radiation. At this rate, the Sun has so far converted around 100 times the mass of Earth into energy, about 0.03% of the total mass of the Sun. The Sun will spend a total of approximately 10 billion years as a main sequence star. The Sun is gradually becoming hotter in its core, hotter at the surface, larger in radius, and more luminous during its time on the main sequence. Since the beginning of its main sequence life, it has expanded in radius by 15%, and the surface has increased in temperature from 5,620 Kelvin to 5,777 Kelvin, resulting in a 48% increase in luminosity from 0.677 solar luminosities to its present-day 1.0 solar luminosity. This occurs because the helium atoms in the core have a higher mean molecular weight than the hydrogen atoms that were fused, resulting in less thermal pressure. The core is therefore shrinking, allowing the outer layers of the Sun to move closer to the centre, releasing gravitational potential energy. According to the virial theorem, half this released gravitational energy goes into heating, which leads to a gradual increase in the rate at which fusion occurs, and thus an increase in the luminosity. This process speeds up as the core gradually becomes denser. At present, it is increasing in brightness by about 1% every 100 million years. Section 7.3. After core hydrogen exhaustion. There's an image, the size of the current Sun, now in the main sequence, compared to its estimated size during its red giant phase in the future. The Sun does not have enough mass to explode as a supernova. Instead, when it runs out of hydrogen in the core in approximately 5 billion years, core hydrogen fusion will stop, and there will be nothing to prevent the core from contracting. The release of gravitational potential energy causes the luminosity of the star to increase, ending the main sequence phase and leading the star to expand over the next billion years, first into a subgiant and then into a red giant. The heating due to gravitational contraction will also lead to hydrogen fusion in a shell just outside the core, where unfused hydrogen remains, contributing to the increased luminosity, which will eventually reach more than 1,000 times its present luminosity. As a red giant, the Sun will grow so large that it will engulf Mercury, Venus, and probably Earth. The Sun will spend around 1 billion years as a red giant branch star and lose around 1/3 of its mass. There's an image, evolution of a Sun-like star. The track of a 1 solar mass star on the Hertzsprung-Russell diagram is shown from the main sequence to the post-asymptotic giant branch stage. After the red giant branch, the Sun has approximately 120 million years of active life left, but much happens. First, the core, full of degenerate helium, ignites violently in the helium flash, where it is estimated that 6% of the core, itself 40% of the Sun's mass, will be converted into carbon within a matter of minutes through the triple alpha process. The Sun then shrinks to around 10 times its current size and 50 times the luminosity, with a temperature a little lower than today. It will then have reached the red clump or horizontal branch, but a star of the Sun's metallicity does not evolve blueward along the horizontal branch. Instead, it just becomes moderately larger and more luminous over about 100 million years as it continues to react helium in the core. When the helium is exhausted, the Sun will repeat the expansion it followed when the hydrogen in the core was exhausted, except that this time it all happens faster and the Sun becomes larger and more luminous. This is the asymptotic giant branch phase, and the Sun is alternately reacting hydrogen in a shell or helium in a deeper shell. After about 20 million years on the early asymptotic giant branch, the Sun becomes increasingly unstable, with rapid mass loss and thermal pulses that increase the size and luminosity for a few hundred years, every 100,000 years or so. The thermal pulses become larger each time, with the later pulses pushing the luminosity to as much as 5,000 times the current level and the radius to over 1 astronomical unit. According to a 2008 model, Earth's orbit will have initially expanded significantly due to the Sun's loss of mass as a red giant, but will later start shrinking due to tidal forces and, eventually, drag from the lower chromosphere, so that it is engulfed by the Sun during the tip of the red giant branch phase, 3.8 and 1 million years after Mercury and Venus have respectively suffered the same fate. Models vary depending on the rate and timing of mass loss. Models that have higher mass loss on the red giant branch produce smaller, less luminous stars at the tip of the asymptotic giant branch, perhaps only 2,000 times the luminosity and less than 200 times the radius. For the Sun, 4 thermal pulses are predicted before it completely loses its outer envelope and starts to make a planetary nebula. By the end of that phase, lasting approximately 500,000 years, the Sun will only have about half of its current mass. The post-asymptotic giant branch evolution is even faster. The luminosity stays approximately constant as the temperature increases, with the ejected half of the Sun's mass becoming ionized into a planetary nebula as the exposed core reaches 30,000 Kelvin. The final naked core, a white dwarf, will have a temperature of over 100,000 Kelvin and contain an estimated 54.05% of the Sun's present-day mass. The planetary nebula will disperse in about 10,000 years, but the white dwarf will survive for trillions of years before fading to a hypothetical black dwarf. Section 8. Motion and Location. The Sun lies close to the inner rim of the Milky Way's Orion Arm, in the local interstellar cloud or the Gould Belt, at a distance of 7.5 to 8.5 kiloparsecs, 24 to 28 kilolight-years, from the galactic centre. The Sun is contained within the local bubble, a space of rarefied hot gas, possibly produced by the supernova remnant Gemenga, or multiple supernovae in subgroup B1 of the Pleiades moving group. The distance between the local arm and the next arm out, the Perseus arm, is about 6,500 light-years. The Sun, and thus the solar system, is found in what scientists call the galactic habitable zone. The apex of the Sun's way, or the solar apex, is the direction that the Sun travels relative to other nearby stars. This motion is towards a point in the constellation Hercules, near the star Vega. Stars within 100 parsecs of the Sun, 326 light-years, have speeds relative to the Sun which can be modelled approximately by a Maxwell-Boltzmann distribution, especially for the lower speeds, or a log-normal distribution, especially for the higher speeds. But with more high-speed stars, greater than 300 km per second, than predicted by either distribution. The mean velocity of these stars, not the mean speed, relative to the Sun, or the mean velocity of the Sun relative to them, is around 20 km per second. Within 32.6 light-years of the Sun, there are 350 known stars in 227 systems as of 2000, including 163 single stars. It is estimated that a further 130 systems within this range have not yet been identified. Out to 81.5 light-years, there may be up to 7,500 stars, of which around 2,600 are known. The number of substellar objects in that volume is expected to be comparable to the number of stars. Of the 50 nearest stellar systems within 17 light-years from Earth, the closest being the red dwarf Proxima Centauri at approximately 4.2 light-years, the Sun ranks 4th in mass. The Gaia catalogue of nearby stars, all within 100 parsecs, contains 331,312 stars, and is thought to include at least 92% of the stars of stellar spectral type M9, or earlier, i.e. hotter. Section 8.1. Orbit in Milky Way. The Sun orbits the centre of the Milky Way, and it is presently moving in the direction of the constellation of Cygnus. A simple model of the motion of a star in the galaxy gives the galactic coordinates x, y, and z as x at time t equals x at time 0 plus u at time 0 over kappa multiplied by sine of kappa t plus v at time 0 divided by 2b all multiplied by 1 minus cosine of kappa t. Then y at time t is equal to y at time 0 plus 2a multiplied by, in brackets, x at time 0 plus v at time 0 over 2b, close the brackets and multiply by t, minus omega 0 divided by b kappa, multiplied by v at time 0 times sine of kappa t, plus 2 omega 0 divided by kappa squared multiplied by u at time 0 multiplied by, in brackets, 1 minus cosine of kappa t. And finally, z at time t is equal to w at time 0 divided by nu multiplied by sine of nu t plus z at time 0 times the cosine of nu t, where u, v and w are the respective velocities with respect to the local standard of rest, a and b are the Oort constants, omega 0 equal to a minus b is the angular velocity of galactic rotation for the local standard of rest, kappa equal to the square root of minus 4 times omega 0 times b is the epicyclic frequency, and nu is the vertical oscillation frequency. For the Sun, the present values of u, v and w are estimated as 10.00, 5.25 and 7.17 kilometers per second respectively, and estimates for the other constants are a being equal to 15.5 kilometers per second per kiloparsec, b is equal to minus 12.2 kilometers per second per kiloparsec, kappa is equal to 37 kilometers per second per kiloparsec, and nu is equal to 74 kilometers per second per kiloparsec. We take x at time 0 and y at time 0 to be 0, and z at time 0 is estimated to be 17 parsecs. This model implies that the Sun circulates around a point that is itself going around the galaxy. The period of the Sun's circulation around the point is 2 pi divided by kappa, which, using the equivalence that a parsec equals 1 kilometer per second times 0.978 million years, comes to 166 million years, shorter than the time it takes for the point to go around the galaxy. In the xy coordinates, the Sun describes an ellipse around the point, whose length in the y direction is 2 times the square root of everything I'm about to say, 2 times omega 0 divided by kappa squared multiplied by u at time 0 all squared, plus omega 0 divided by b kappa times v at time 0 all squared. And that is all equal to 1035 parsecs, and whose width in the x direction is 2 times the square root of everything I'm about to say, u at time 0 divided by kappa all squared, plus v at time 0 divided by 2b all squared, and that is equal to 691 parsecs. The ratio of length to width of this ellipse, the same for all stars in our neighbourhood, is 2 omega divided by kappa, which is approximately equal to 1.50. The moving point is presently at x equal to v at time 0 over 2b equals minus 215 parsecs, and y is equal to 2 times omega 0 divided by kappa squared times u at time 0, which is equal to 405 parsecs. The oscillation in the z direction takes the Sun, the square root of everything I'm about to say, w at time 0 divided by nu all squared, plus z at time 0 squared, which is equal to 98 parsecs above the galactic plane, and the same distance below it, with a period of 2 pi over nu, or 83 million years, approximately 2.7 times per orbit. Although 2 pi over omega 0 is 222 million years, the value of omega at the point around which the Sun circulates is omega approximately equal to omega 0 minus 2a over r0 times delta x, which is approximately equal to 26.1 kilometers per second per kiloparsec. See Oort constants, corresponding to 235 million years, and this is the time that the point takes to go once around the galaxy. Other stars with the same value of x plus v over 2b have to take the same amount of time to go around the galaxy as the Sun, and thus remain in the same general vicinity as the Sun. The Sun's orbit around the Milky Way is perturbed due to the non-uniform mass distribution in the Milky Way, such as that in and between the galactic spiral arms. It has been argued that the Sun's passage through the higher density spiral arms often coincides with mass extinctions on Earth, perhaps due to increased impact events. It takes the solar system about 225 to 250 million years to complete one orbit through the Milky Way, a galactic year, so it is thought to have completed 20 to 25 orbits during the lifetime of the Sun. The orbital speed of the solar system about the centre of the Milky Way is approximately 251 kilometers per second, or 156 miles per second. At this speed, it takes around 1,190 years for the solar system to travel a distance of 1 light year, or 7 days to travel 1 astronomical unit. The Milky Way is moving with respect to the cosmic microwave background radiation, CMB, in the direction of the constellation Hydra, with a speed of 550 kilometers per second, and the Sun's resultant velocity with respect to the cosmic microwave background is about 370 kilometers per second in the direction of Crater or Leo. Section 8.2. Motion in the solar system. The Sun is moved by the gravitational pull of the planets. One can think of the barycenter of the solar system as being stationary, or as moving in a steady motion around the galaxy. The centre of the Sun is always within 2.2 solar radii of the barycenter. This motion of the Sun is mainly due to Jupiter, Saturn, Uranus and Neptune. For some periods of several decades, the motion is rather regular, forming a trefoil pattern, whereas between these periods it appears more chaotic. After 179 years, 9 times the synodic period of Jupiter and Saturn, the pattern more or less repeats, but rotated by about 24 degrees. The orbits of the inner planets, including of the Earth, are similarly displaced by the same gravitational forces, so the movement of the Sun has little effect on the relative positions of the Earth and the Sun, or on solar irradiance on the Earth as a function of time. Section 9. Theoretical problems. There's an image, map of the full Sun by stereo and SDO spacecraft. Section 9.1. Coronal heating problem. Main article, stellar corona. The temperature of the photosphere is approximately 6,000 Kelvin, whereas the temperature of the corona reaches 1 million to 2 million Kelvin. The high temperature of the corona shows that it is heated by something other than direct heat conduction from the photosphere. It is thought that the energy necessary to heat the corona is provided by turbulent motion in the convection zone below the photosphere, and 2 main mechanisms have been proposed to explain coronal heating. The first is wave heating, in which sound, gravitational or magnetohydrodynamic waves are produced by turbulence in the convection zone. These waves travel upward and dissipate in the corona, depositing their energy in the ambient matter in the form of heat. The other is magnetic heating, in which magnetic energy is continuously built up by photospheric motion and released through magnetic reconnection in the form of large solar flares and myriad similar but smaller events, nanoflares. Currently, it is unclear whether waves are an efficient heating mechanism. All waves except Alfvén waves have been found to dissipate or refract before reaching the corona. In addition, Alfvén waves do not easily dissipate in the corona. Current research focus has therefore shifted towards flare heating mechanisms. Section 9.2. Faint young sun problem. Main article, Faint young sun paradox. Theoretical models of the Sun's development suggest that 3.8 to 2.5 billion years ago, during the Archean eon, the Sun was only about 75% as bright as it is today. Such a weak star would not have been able to sustain liquid water on Earth's surface, and thus life should not have been able to develop. However, the geological record demonstrates that Earth has remained at a fairly constant temperature throughout its history, and that the young Earth was somewhat warmer than it is today. One theory among scientists is that the atmosphere of the young Earth contained much larger quantities of greenhouse gases, such as carbon dioxide and methane, than are present today, which trapped enough heat to compensate for the smaller amount of solar energy reaching it. However, examination of Archean sediments appears inconsistent with the hypothesis of high greenhouse concentrations. Instead, the moderate temperature range may be explained by a lower surface albedo, brought about by less continental area and the lack of biologically induced cloud condensation nuclei. This would have led to increased absorption of solar energy, thereby compensating for the lower solar output. Section 10. Observational History. Section 10.1. Early Understanding. See also The Sun in Culture. There's an image. The Trundholm Sun Chariot, pulled by a horse, is a sculpture believed to be illustrating an important part of Nordic Bronze Age mythology. The sculpture is probably from circa 1350 BC. It is displayed at the National Museum of Denmark. The sun has been an object of veneration in many cultures throughout human history. Humanity's most fundamental understanding of the sun is as the luminous disk in the sky, whose presence above the horizon causes day and whose absence causes night. In many prehistoric and ancient cultures, the sun was thought to be a solar deity or other supernatural entity. The sun has played an important part in many world religions, as described in a later section. Section 10.2 Development of Scientific Understanding. In the early 1st millennium BC, Babylonian astronomers observed that the sun's motion along the ecliptic is not uniform, though they did not know why. It is today known that this is due to the movement of the Earth in an elliptic orbit around the sun, with Earth moving faster when it is nearer to the sun at perihelion and moving slower when it is farther away at aphelion. One of the first people to offer a scientific or philosophical explanation for the sun was the Greek philosopher Anaxagoras. He reasoned that it was not the chariot of Helios, but instead a giant flaming ball of metal even larger than the land of the Peloponnesus, and that the moon reflected the light of the sun. For teaching this heresy, he was imprisoned by the authorities and sentenced to death, though he was later released through the intervention of Pericles. Eratosthenes estimated the distance between Earth and the sun in the 3rd century BC as of stadia myriads 480,000, the translation of which is ambiguous, implying either 4,080,000 stadia, 755,000 kilometers, or 804 million stadia, 148 to 153 million kilometers, or 0.99 to 1.02 astronomical units. The latter value is correct to within a few percent. In the 1st century AD, Ptolemy estimated the distance as 1,210 times the radius of Earth, approximately 7.71 million kilometers, 0.0515 astronomical units. The theory that the sun is the centre around which the planets orbit was first proposed by the ancient Greek Aristarchus of Samos in the 3rd century BC, and later adopted by Seleucus of Seleucia, see heliocentrism. This view was developed in a more detailed mathematical model of a heliocentric system in the 16th century by Nicolaus Copernicus. Observations of sunspots were recorded during the Han Dynasty, 206 BC to AD 220, by Chinese astronomers, who maintained records of these observations for centuries. Averroes also provided a description of sunspots in the 12th century. The invention of the telescope in the early 17th century permitted detailed observations of sunspots by Thomas Harriot, Galileo Galilei, and other astronomers. Galileo posited that sunspots were on the surface of the sun rather than small objects passing between Earth and the sun. Arabic astronomical contributions include al-Battani's discovery that the discovery of the sun's apogee, the place in the sun's orbit against the fixed stars where it seems to be moving the slowest, is changing. In modern heliocentric terms, this is caused by a gradual motion of the aphelion of the Earth's orbit. Ibn Yunus observed more than 10,000 entries for the sun's position for many years using a large astrolabe. From an observation of a transit of Venus in 1032, the Persian astronomer and polymath Ibn Sina concluded that Venus is closer to Earth than the Sun. In 1672, Giovanni Cassini and John Richter determined the distance to Mars and were thereby able to calculate the distance to the Sun. There's an image, Sol, the Sun, from a 1550 edition of Guido Bonatti's Liber Astronomiae. In 1666, Isaac Newton observed the sun's light using a prism, and showed that it is made up of light of many colours. In 1800, William Herschel discovered infrared radiation beyond the red part of the solar spectrum. The 19th century saw advancement in spectroscopic studies of the sun. Joseph von Fraunhofer recorded more than 600 absorption lines in the spectrum, the strongest of which are still often referred to as Fraunhofer lines. In the early years of the modern scientific era, the source of the sun's energy was a significant puzzle. Lord Kelvin suggested that the sun is a gradually cooling liquid body that is radiating an internal store of heat. Kelvin and Hermann von Helmholtz then proposed a gravitational contraction mechanism to explain the energy output, but the resulting age estimate was only 20 million years, well short of the time span of at least 300 million years suggested by some geological discoveries of that time. In 1890, Joseph Lockyer, who discovered helium in the solar spectrum, proposed a meteoritic hypothesis for the formation and evolution of the Sun. Not until 1904 was a documented solution offered. Ernest Rutherford suggested that the Sun's output could be maintained by an internal source of heat, and suggested radioactive decay as the source. However, it would be Albert Einstein who would provide the essential clue to the source of the Sun's energy output, with his mass-energy equivalence relation E equals mc squared. In 1920, Sir Arthur Eddington proposed that the pressures and temperatures at the core of the Sun could produce a nuclear fusion reaction that merged hydrogen, protons, into helium nuclei, resulting in a production of energy from the net change in mass. The preponderance of hydrogen in the Sun was confirmed in 1925 by Cecilia Payne using the ionization theory developed by Meghnad Saha. The theoretical concept of fusion was developed in the 1930s by the astrophysicists Subramanian Chandrasekhar and Hans Bethe. Hans Bethe calculated the details of the two main energy-producing nuclear reactions that power the Sun. In 1957, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle showed that most of the elements in the universe have been synthesized by nuclear reactions inside stars, some like the Sun. Section 10.3 Solar Space Missions. See also Solar Observatory. There's a video, a lunar transit of the Sun captured during calibration of Stereo B's ultraviolet imaging cameras. There's then an image, the Sun giving out a large geomagnetic storm at 1:29 p.m. EST, 13th of March 2012. The first satellites designed for long-term observation of the Sun from interplanetary space were NASA's Pioneers 6, 7, 8 and 9, which were launched between 1959 and 1968. These probes orbited the Sun at a distance similar to that of Earth, and made the first detailed measurements of the solar wind and the solar magnetic field. Pioneer 9 operated for a particularly long time, transmitting data until May 1983. In the 1970s, two Helios spacecraft and the Skylab Apollo telescope mount provided scientists with significant new data on solar wind and the solar corona. The Helios 1 and 2 probes were US-German collaborations that studied the solar wind from an orbit carrying the spacecraft inside Mercury's orbit at perihelion. The Skylab space station, launched by NASA in 1973, included a solar observatory module called the Apollo telescope mount that was operated by astronauts resident on the station. Skylab made the first time-resolved observations of the solar transition region and of ultraviolet emissions from the solar corona. Discoveries include the first observations of coronal mass ejections, then called coronal transients, and of coronal holes, now known to be intimately associated with the solar wind. There's an image. Coronal hole on the Sun forms a question mark. 22nd of December 2017. In 1980, the Solar Maximum mission was launched by NASA. This spacecraft was designed to observe gamma rays, X-rays and ultraviolet radiation from solar flares during a time of high solar activity and solar luminosity. Just a few months after launch, however, an electronics failure caused the probe to go into standby mode, and it spent the next 3 years in this inactive state. In 1984, Space Shuttle Challenger mission STS-41C retrieved the satellite and repaired its electronics before re-releasing it into orbit. The Solar Maximum mission subsequently acquired thousands of images of the solar corona before re-entering Earth's atmosphere in June 1989. Launched in 1991, Japan's Yohkoh Sunbeam satellite observed solar flares at X-ray wavelengths. Mission data allowed scientists to identify several types of flares and demonstrated that the corona away from regions of peak activity was much more dynamic and active than had previously been supposed. Yohkoh observed an entire solar cycle, but went into standby mode when an annual eclipse in 2001 caused it to lose its lock on the Sun. It was destroyed by atmospheric re-entry in 2005. One of the most important solar missions to date has been the Solar and Heliospheric Observatory, jointly built by the European Space Agency and NASA and launched on the 2nd of December 1995. Originally intended to serve a 2-year mission, a mission extension through 2012 was approved in October 2009. It has proven so useful that a follow-on mission, the Solar Dynamics Observatory, was launched in February 2010. Situated at the Lagrangian point between the Earth and the Sun, at which the gravitational pull from both is equal, SOHO has provided a constant view of the Sun at many wavelengths since its launch. Besides its direct solar observation, SOHO has enabled the discovery of a large number of comets, mostly tiny sun-grazing comets that incinerate as they pass the Sun. There's an image. A solar prominence erupts in August 2012, as captured by SDO. All these satellites have observed the Sun from the plane of the ecliptic, and so have only observed its equatorial regions in detail. The Ulysses probe was launched in 1990 to study the Sun's polar regions. It first travelled to Jupiter to slingshot into an orbit that would take it far above the plane of the ecliptic. Once Ulysses was in its scheduled orbit, it began observing the solar wind and magnetic field strength at high solar latitudes, finding that the solar wind from high latitudes was moving at about 750 km per second, which was slower than expected, and that there were large magnetic waves emerging from high latitudes that scattered galactic cosmic rays. Elemental abundances in the photosphere are well known from spectroscopic studies, but the composition of the interior of the Sun is more poorly understood. A solar wind sample return mission, GENESIS, was designed to allow astronomers to directly measure the composition of solar material. The Solar Terrestrial Relations Observatory, STEREO, mission was launched in October 2006. 2 identical spacecraft were launched into orbits that caused them to, respectively, pull further ahead of and fall gradually behind Earth. This enables stereoscopic imaging of the Sun and solar phenomena, such as coronal mass ejections. The Parker Solar Probe was launched in 2018 aboard a Delta IV Heavy rocket, and will reach a perigee of 0.046 astronomical units in 2025, making it the closest orbiting man-made satellite as the first spacecraft to fly low into the solar corona. The Indian Space Research Organisation has scheduled the launch of a 100-kilogram satellite named Aditya for mid-2020. Its main instrument will be a coronagraph for studying the dynamics of the solar corona. Section 11. Observation and Effects. There's an image. During certain atmospheric conditions, the Sun becomes visible to the naked eye and can be observed without stress on the eyes. You can click on the photo to see the full cycle of a sunset, as observed from the high plains of the Mojave Desert. There's another image. The Sun as seen from low Earth orbit overlooking the International Space Station. This sunlight is not filtered by the lower atmosphere, which blocks much of the solar spectrum. The brightness of the Sun can cause pain from looking at it with the naked eye. However, doing so for brief periods is not hazardous for normal, non-dilated eyes. Looking directly at the Sun causes phosphine visual artifacts and temporary partial blindness. It also delivers about 4 milliwatts of sunlight to the retina, slightly heating it and potentially causing damage in eyes that cannot respond properly to the brightness. Ultraviolet exposure gradually yellows the lens of the eye over a period of years, and it is thought to contribute to the formation of cataracts, but this depends on general exposure to solar UV, and not whether one looks directly at the Sun. Long-duration viewing of the direct Sun with the naked eye can begin to cause UV-induced sunburn-like lesions on the retina after about 100 seconds, particularly under conditions where the UV light from the Sun is intense and well focused. Conditions are worsened by young eyes or new lens implants, which emit more UV than aging natural eyes, sun angles near the zenith, and observing locations at high altitude. Viewing the Sun through light-concentrating optics such as binoculars may result in permanent damage to the retina without an appropriate filter that blocks UV and substantially dims the sunlight. When using an attenuating filter to view the Sun, the viewer is cautioned to use a filter specifically designed for that use. Some improvised filters that pass ultraviolet or infrared rays can actually harm the eye at high brightness levels. Herschel wedges, also called solar diagonals, are effective and inexpensive for small telescopes. The sunlight that is destined for the eyepiece is reflected from an unsilvered surface of a piece of glass. Only a very small fraction of the incident light is reflected. The rest passes through the glass and leaves the instrument. If the glass breaks because of the heat, no light at all is reflected, making the device fail-safe. Simple filters made of darkened glass allow the full intensity of sunlight to pass through if they break, endangering the observer's eyesight. Unfiltered binoculars can deliver hundreds of times as much energy as using the naked eye, possibly causing immediate damage. It is claimed that even brief glances at the midday sun through an unfiltered telescope can cause permanent damage. There's an image, halo with sun dogs. Partial solar eclipses are hazardous to view because the eye's pupil is not adapted to the unusually high visual contrast. The pupil dilates according to the total amount of light in the field of view, not the brightest object in the field. During partial eclipses, most sunlight is blocked by the moon passing in front of the sun, but the uncovered parts of the photosphere have the same surface brightness as during a normal day. In the overall gloom, the pupil expands from about 2 mm to about 6 mm, and each retinal cell exposed to the solar image receives up to 10 times more light than it would looking at the non-eclipsed sun. This can damage or kill those cells, resulting in small permanent blind spots for the viewer. The hazard is insidious for inexperienced observers and for children because there is no perception of pain. It is not immediately obvious that one's vision is being destroyed. There are two images, a sunrise and a sunset in Thailand in summer. During sunrise and sunset, sunlight is attenuated because of Rayleigh scattering and maze scattering from a particularly long passage through Earth's atmosphere, and the sun is sometimes faint enough to be viewed comfortably with the naked eye or safely with optics, provided there is no risk of bright sunlight suddenly appearing through a break between clouds. Hazy conditions, atmospheric dust, and high humidity contribute to this atmospheric attenuation. An optical phenomenon known as a green flash can sometimes be seen shortly after sunset or before sunrise. The flash is caused by light from the sun just below the horizon being bent, usually through a temperature inversion, towards the observer. Light of shorter wavelengths, violet, blue, green, is bent more than that of longer wavelengths, yellow, orange, red, but the violet and blue light is scattered more, leaving light that is perceived as green. Ultraviolet light from the sun has antiseptic properties and can be used to sanitize tools and water. It also causes sunburn and has other biological effects, such as the production of vitamin D and sun tanning. It is also the main cause of skin cancer. Ultraviolet light is strongly attenuated by Earth's ozone layer, so that the amount of ultraviolet varies greatly with latitude and has been partially responsible for many biological adaptations, including variations in human skin colour in different regions of the Earth. Section 12. Planetary System, for which the main article is Solar System. There's an image, size comparison of the Sun and its planets. Clickable. The Sun has 8 known planets. This includes 4 terrestrial planets, Mercury, Venus, Earth and Mars, 2 gas giants, Jupiter and Saturn, and 2 ice giants, Uranus and Neptune. The solar system also has at least 5 dwarf planets, an asteroid belt, numerous comets, and a large number of icy bodies which lie beyond the orbit of Neptune. Section 13. Religious Aspects, for which the main article is Solar Deity. Solar deities play a major role in many world religions and mythologies. Worship of the sun was central to civilizations such as the ancient Egyptians, the Inca of South America, and the Aztecs of what is now Mexico. In religions such as Hinduism, the sun is still considered a god. Many ancient monuments were constructed with solar phenomena in mind. For example, stone megaliths accurately mark the summer or winter solstice. Some of the most prominent megaliths are located in Nabta Playa, Egypt, Mnastra in Malta, and at Stonehenge in England. Newgrange, a prehistoric human-built mound in Ireland, was designed to detect the winter solstice. The Pyramid of El Castillo at Chichen Itza in Mexico is designed to cast shadows in the shape of serpents climbing the pyramid at the vernal and autumnal equinoxes. The ancient Sumerians believed that the sun was Utu, the god of justice and twin brother of Inanna, the queen of heaven, who was later identified as the planet Venus. Later, Utu was identified with the East Semitic god Shamash. Utu was regarded as a helper deity who aided those in distress, and, in iconography, he is usually portrayed with a long beard and clutching a saw, which represented his role as the dispenser of justice. From at least the 4th dynasty of ancient Egypt, the sun was worshipped as the god Ra, portrayed as a falcon-headed divinity surmounted by the solar disk and surrounded by a serpent. In the New Empire period, the sun became identified with the dung beetle, whose spherical ball of dung was identified with the sun. In the form of the sun disk Aten, the sun had a brief resurgence during the Amarna period, when it again became the preeminent, if not only, divinity for the pharaoh Akhenaton. The Egyptians portrayed the god Ra as being carried across the sky in a solar bark, accompanied by lesser gods, and to the Greeks he was Helios, carried by a chariot drawn by fiery horses. From the reign of Elagabalus in the late Roman Empire, the sun's birthday was a holiday celebrated as Sol Invictus, literally unconquered sun, soon after the winter solstice, which may have been an antecedent to Christmas. Regarding the fixed stars, the sun appears from Earth to revolve once a year along the ecliptic through the zodiac, and so Greek astronomers categorized it as one of the 7 planets. Greek planetes, wanderer. The naming of the days of the weeks after the 7 planets dates to the Roman era. In Proto-Indo-European religion, the sun was personified as the goddess Sahul. Derivatives of this goddess in Indo-European languages included the Old Norse Sol, Sanskrit Surya, Gaulish Sulis, Lithuanian Sole, and Slavic Solntse. In ancient Greek religion, the sun deity was the male god Helios, who in later times was syncretized with Apollo. In the Bible, Malachi chapter 4 verse 2 mentions the Sun of Righteousness, sometimes translated as the Sun of Justice, which some Christians have interpreted as a reference to the Messiah, Christ. In ancient Roman culture, Sunday was the day of the sun god. It was adopted as the Sabbath day by Christians who did not have a Jewish background. The symbol of light was a pagan device adopted by Christians, and perhaps the most important one that did not come from Jewish traditions. In paganism, the sun was a source of life, giving warmth and illumination to mankind. It was the centre of a popular cult among Romans, who would stand at dawn to catch the first rays of sunshine as they prayed. The celebration of the winter solstice, which influenced Christmas, was part of the Roman cult of the unconquered sun, Sol Invictus. Christian churches were built with an orientation so that the congregation faced towards the sunrise in the east. Tonatiuh, the Aztec god of the sun, was usually depicted holding arrows and a shield, and was closely associated with the practice of human sacrifice. The sun goddess Amaterasu is the most important deity in the Shinto religion, and she is believed to be the direct ancestor of all Japanese emperors. This sound file and all text in the article are licensed under the Creative Commons Attribution Share-alike 3.0 Unported License, available at creativecommons.org/licenses/by-sa/3.0.